Hello everyone. This is the second to the last video for the first grading period. This video specifically concerned on the practice exercises and demonstrations on the second practice exercise of lesson number 2 on the scientific notation of unit number 4. In the previous video, we were able to discuss the significant figures or the significant digits of the standard forms of real numbers. As to why we need to determine the exact number of significant figures and significant digits, it is because they are actually needed when writing the standard forms of the scientific notations of the real numbers from its standard form. So to express what I am talking about, let me share to you our practice exercise here. So I have here seven different real numbers in their standard form. When you say standard form, they're actually in any form such as in integers or numbers in decimal notation, etc., etc. Okay. So we have here the numbers 1 to 7. So let me copy here number 1 so that we could actually um, illustrate. So you have 1,572.33. So before we write it in scientific notation, we need to determine first the number of significant figures or significant digits. Since all of the digits here are non-zero, in short, all of the digits here are significant. Therefore, we have here six significant digits or significant figures. Um, The purpose again of this identifying significant digits is for us to be guided that when we write out this number in its scientific notation, it should also contain six significant figures. But how do we write numbers in scientific notations? First is to actually, we need to create a um, expression wherein we only have one value for an integer and the rest may be a decimal places. In short, we need to make this, instead of 1,572.33, we need to make this 1 point something. So 1 would be our integral value and the remaining numbers would be all in decimal places. So in short, we are going to move this to the right 3 times. 1, 2, 3. Thereby making 1.5. That's 1.57233. So we have this first step. We have moved the decimal notation to the right. But the scientific notation is basically in the form of A. Let us have A, yeah, times have 10 to the power of n. N meaning the number of movements your decimal point took. A, this will be the result here of the value. So 10 is just a multiplier here. So this would be equal to, okay, let's continue with number 1 times 10 to the power of how many steps? 3. 1, 2, 3. So you have here 3 steps. But we are not yet done because we need to specify the movement. When we move our value here, our decimal point, I mean, to the right from a standard form to a scientific notation, we have gained three different multipliers of 10. Okay? Gained, meaning the answer is positive 3. Why gain? Take note that in the given, it's 1,000. 1,000 is actually 10 cubed or 10 times 10 times 10. So it's positive. But when we move this to the right, that is the time that we are, I mean the right, yes, that is now the time that the movement becomes negative because we have lost multipliers of 10. Or in short, we reach tens, hundreds, thousands. This is the answer for number 1. Number two. Number two is for simple. By the way, before we go to number two, let's check if this scientific notation still contains six significant figures. In scientific notation, this expression here, though numbers, will not be counted as significant digits because they are not digits, they are just multiplier. So here, let's try. I still have one, two, three, four, five, six, and all of them are significant digits. So we still retain the six significant digits here. So for number two, you have 408. So we have three significant digits because again, the zero in the middle between the middle of 4 and 8 are also counted. So take note that we are going to take three significant digits when we deal with scientific notation still. So let us now try to make it in scientific notation, but we don't have a decimal point here. This being an integer automatically means that we have here a decimal point here. Okay. Okay. We have a decimal point there, and that is the decimal point that we are going to move so that we can only retain one integral value. Again, we have three significant digits here. So this will become 4.08, and then use the multiplier times 10 to the power of the number of steps, 1 and 2. So 1 and 2. So how many significant digits are there in scientific notation? One, two, three. So we retain the significant figure or digits, which is 3. So that is actually the concern. We will need to retain the significant digits and significant figures, unless I am going to make a disclaimer. Unless in number one there would be an instruction to give the scientific notation in two decimal places. So you're not going to round it off, removing the remaining three, unless there's an instruction. But if there are no instructions, we stay with the number of significant figures, which is the more appropriate one. Number three. So you have number three, you have 0.001000. Okay. So we are now going to determine first the significant figures. Significant figures, 1. Okay, we have one significant figure. The leading zeros will be not, but the trailing zeros, because we have here decimal point, will also be counted. In short, we have four significant figures here. And then as we make our scientific notation, we will now move the decimal point. Not here, because if we are going to move a decimal point here, look at it. If we're going to point a decimal point here, we cannot look for an integral value because, of course, this does still zero for excluding number three because that's the item number. 0, 0. There's no integral value here. The integral value will only come in if we're going to move the decimal point until here. So we could have an integral value. This would become 1. 1. How many steps? A multiplier times 10. How many movements? 3. But since we move now to the right, but as we move to the right, we lost, not necessarily lost. I'm just using the word loss so that we could actually understand it better. We lost multipliers of 10 because this is actually tens, hundreds, and thousands. They are divisions of tens. So we lost. So this is now the reason why it's negative. Why do I skip a space here? Because when we go back to the significant figures, there should be 4. There should be 4 significant figures. So this only has 1. How to come up with 4 significant figures? The 4 significant figures will be covered by the remaining zeros. We have to place the zeros there, right? Because by placing the zeros, 1, 2, 3, take note that in the rules of significant figures, this trailing zeros will still be counted as significant figures. So you have 1, 2, 3, 4. We retained the numbers of significant figures. Yeah, it seems a little bit awkward to still write 1.000 because again, you might say they don't matter. But as for the concept of significant figures, they do matter. They matter. So they will be counted. Number four. Number four is shorter. So you have 0.1. How many significant figures? You only have one. Again, the leading zero is not counted. So you have one. And how many movements do you need to gain to gain a um, integral value? One step. So this would become 1 times 10 to the power of how many steps? 1 to the left, negative. Again, we lost multiplier of 10. You may answer here 1.0, 1 point if you will, if you want to, because it still has one significant figure. But do not write 1.0 there, because this will now have two significant figures, wherein in the given standard form you only have one. So better yet, do not write any more decimal notation there. Simply replace 1 times 10 to the power of negative 1. That's it. Number 5. Number 5 is 2,300. 2,300 has significant figures 1 and 2. Are these two significant? Are those two significant? The answer is no, because we don't have a decimal. We don't have the notation for decimal place here. So they are considered to be trailing zeros. So they are not counted. So we only have two significant figures. But sir, how do we create scientific notation if we don't have a decimal point here? Do not get me wrong. In identifying significant figures or significant digits, this has no decimal point. And that is why we only have two significant figures. But when writing in scientific notation, we could write here a decimal point, not to change the number of the significant figures, but just to create the movement as to 1, 2, 3. This is actually 2.3, because you only need two. That's significant figures. Do not add 0, 0, because they may be counted as significant. And then times 10 to the power of 1, 2, 3 steps. And then movement to the right, positive. Okay, positive. This is the answer. Again, not get me wrong. Yes, in identifying significant figures or digits, this has no decimal point. Therefore, we only have two significant figures. But when writing scientific notation, just to um, just to account the movements of the decimal point, we may place it here and then move it. Number 6. Number 6 is 00.2020. So I given in your previous practice exercise that the leading zeros will not be counted significant, but the trailing zeros here will be. So it has 1, 2, 3, 4. 4 significant figures. And then we will move the decimal point only once. So this would become 2 point. Please make sure to retain the four significant figures. If you will say 2.02, it's still just 3. You still need to add the remaining 0. Again, the purpose is to retain the number of significant figures, unless there is instruction to round it off to two decimal places, but there's none. So retain. Times 10. How many movement? 1 to the left. We lost a multiplier of 10. So you have negative 1. And for final last item for this practice exercise, you have 1, 2, 3, 4, 4, 3, 2, 0, 1, 1, 2, 3. Okay. In the previous exercise, we have determined that this has only 5. 1, 2, 3, 4, 5. These are leading zeros, not counted. These are trailing zeros, but since there is no decimal point here, they are not counted. So we only have 5 significant figures. Again, just like in number five, yes, for the purpose of significant figures, there's no decimal point there. But for the purpose of writing in scientific notation, we may place it here and then move 1, 2, 3, 4, 5, 6, 7 until we get an integral value. This would become 4.3201. Five only significant figures. Do not add the remaining zeros because we only need 5 times 10 to the power of how many steps? 1, 2, 3, 4, 5, 6, 7. Going to the right, we gained multiplier of 10 positive. So this is the scientific notation for number 7. The sole purpose of scientific notation is actually on writing very large and very minute or very small numbers, real numbers, into a condensed form, right? Because there are plenty of expressions that are plenty of real numbers. If you're going to deal with the chemistry, science, branches of sciences, physics, you might notice some numbers in very long numbers. When you talk about size of an atom, when you talk about the distance of the sun, approximate distance of the earth, the sun, and so on and so forth, just like the items I have presented in the module. We can just simply write it into a scientific notation to a condensed form, which is easier to understand. Okay, that's the purpose of scientific notation. The next video, which is our last video, would be the reverse of this. We will be giving you scientific notations, and return. We ask you. We will ask. We will try to return to the standard form of the real numbers. Thank you very much. Hopefully, you've enjoyed. Use this as part of your review. Goodbye.